So, keeping an eye on the universe. What telescopes tell us about how the universe works. So Galileo first turned his telescope on the sky some 400 or so years ago, and ever since then telescopes have been evolving. Originally using lenses to focus the light, but thereafter it was realised that mirrors could do a better job, especially when telescopes grew in size and produced larger and larger instruments. If we look at what happened last century, we were getting monsters like this, the Hooker telescope with a mirror 2.5 meters in diameter, and then the Hale telescope with a mirror 5 meters in diameter. That was the largest telescope in the world when I was born, and it was the largest telescope in the world probably for most of my adult life. Now we've got used to the ideas of telescopes in space, such as the Hubble Space Telescope and the James Webb Space Telescope, launched just a few years ago. And it won't be long before we have some really big telescopes coming online on the Earth, such as, for instance, the European Extremely Large Telescope. A bit of a crazy name, but at least it describes the relative size of telescopes like this. Huge mirrors, absolutely humongous mirrors compared to the telescopes of a few hundred years ago. This gives us an idea of how the sizes of telescopes have changed. Here we're looking to scale at the size of the mirrors of various telescopes. In the top left-hand corner, we have the last of the largest refracting telescopes that used lenses to focus the light, the Yerkes Observatory refractor and a similar telescope in a Paris exhibition. These were about 1 meter or so in diameter, but you can see on this scale they are tiny compared to the huge mirrors of telescopes that have evolved over the last century or so. And to get an idea of scale, it might help to realise that in the bottom left-hand corner there's a tennis court to scale, and in the bottom right-hand corner there's a basketball court to scale. And if your screen is good enough, you can perhaps see a human here which is attempting to give us some sort of scale. So the largest telescope in the world at the moment is Gran Telescopio Canarias, as indicated by the red box at the top there. It's made of hexagonal segments rather than one large circular mirror, but we can still approximate it to a circle and say it's got a diameter of about 10 meters or so. By no means the largest that is planned, but at the moment the largest operational telescope. In the bottom left-hand corner, we have telescopes that have been into space, such as the Hubble Space Telescope and the James Webb Space Telescope. Notice that although they are very large compared to refracting telescopes of old that used to use lenses, they are still relatively small compared to some of the huge telescopes that either currently exist on the ground or are planned to be on mountaintops in years to come. That's simply an indication of the difficulty of getting large telescopes onto the top of a rocket and sending them up into space. So we're used to the idea of the Hubble telescope. It's been around for quite a number of decades now. It was launched in 1990, so it's now 35 years old. It's getting to be quite an old piece of scientific equipment, and yet it's still producing amazing results. Such as, for instance, the Hubble Deep Field. It looked into the distant universe, took a very long exposure, and got an idea of just how many galaxies are out there. We figured that the universe is full of galaxies, but it was difficult to get a feel for how many until we had acquired the Hubble Deep Field. An exposure of quite a few days pointing at nowhere in particular, and this particular field of view has happened to catch perhaps a couple of stars in the Milky Way. So these are stars that belong to our own galaxy. It looks like there's at least 2 or 3 of them in this particular image. But essentially everything else in the image is a more distant galaxy. Some of them millions of light years away, some of them perhaps billions of light years away. If we realise that that image was only a tiny patch of sky, if we think about how large a field of view the Hubble Space Telescope has, it's only the size of that red rectangle there when we think of it to scale with the moon in terms of how much sky do we actually image. In other words, it's a tiny, tiny, tiny fraction of the whole sky. So when we see wonderful images of either individual nebulae or galaxies, we have to remind ourselves that they are very small or very remote, or both, because the Hubble Space Telescope only has a tiny field of view. And yet, in the previous image, we saw that there were thousands of galaxies within that tiny field of view. And that tells us, roughly speaking, how many galaxies there must be in the observable universe. And it turns out to be certainly not just millions, it is many billions, possibly even 1 trillion galaxies are out there to be observed if we've got the right telescopes. Here's another ultra deep field, in other words another deep field, another long exposure of a patch of sky in which there was thought to be nothing in particular there. This is pointing in a different patch of sky to make sure that the previous image of a deep field was not just a fluke. Yes, these galaxies are essentially everywhere. No matter which way we point our telescope, if we take a long enough exposure, we find that there are thousands of galaxies even in that tiny patch of sky. And again, this particular field of view is showing perhaps 2 stars in our own Milky Way. Every other object, all of those thousands of smudges and dots, are all galaxies in their own right. If we look at a much closer galaxy, here's a Hubble Space Telescope image of a galaxy that's essentially on our doorstep. It's not at the other side of the observable universe. It's only a few million light years away, which is close on a cosmic scale. And when galaxies are this close, we can see an enormous amount of detail. And the Hubble has allowed us to get a handle on galaxy evolution by seeing galaxies in extreme detail. Many of the galaxies have been seen to be interacting with their neighbours, as these 2 galaxies, the one at the top that looks like it used to be a nice spiral galaxy which has now had its arms distorted, and an even more distorted galaxy at the bottom of the image. This particular pair is known as the rose galaxies. Perhaps you can see why. It looks like this is much more common than we first thought. Whenever we look out into the universe, we find lots of galaxies that are interacting with their neighbours. And we think that that is an important, nay, essential element of how galaxies evolve. They interact with their neighbours and they merge and collide with each other. And that is how galaxies evolve. That's how galaxies grow, by effectively stealing stars from other galaxies. This particular pair of galaxies, called the antenna galaxies, is the result of 2 galaxies colliding with each other. That's not as cataclysmic as it sounds, because when galaxies get close enough to interact with each other, they start producing tidal effects, which actually encourages new star formation. These pink areas that you can see are areas where new stars are being born. So when 2 galaxies collide, it actually triggers the formation of new stars. So galaxy collisions are not the end of life of galaxies, it's part of their evolution. When we look inside our own galaxy to get an idea of how individual stars are behaving rather than collections of stars on the galactic scale, we see various nebula, including this rather wonderful nebula called the Helix Nebula. This is the result of a star coming to the end of its life, swelling up as a red giant, and then effectively shrugging off the outer atmosphere of the star to produce this rather beautiful nebula. And what's left of the core of the star is visible right at the center there. That's the core of the original star, and most of the atmosphere of the star has now been shrugged off to produce this nebula over perhaps many thousands or tens of thousands or perhaps hundreds of thousands of years. This is ultimately the fate of our own sun. We are fairly sure that this star is very similar to our own, and in a few billion years' time, not just yet, but in a few billion years' time, our sun will run out of its hydrogen fuel and will undergo the same change, the same expansion into a red giant phase, and ultimately production of a nebula like this. So in a sense, we're seeing what the sun will look like in a few billion years' time. More massive stars might end their lives not by just shrugging off some of their outer layers, but undergoing a supernova explosion, which effectively redistributes all, or at least most, of the matter of the star throughout interstellar space. And that's what's happened in this particular case, in this nebula called the Crab Nebula in the constellation of Taurus. the Hubble Space Telescope. This is a large object, so the Hubble Space Telescope had to take a mosaic to get the entire object imaged. And we'll have another look at this in just a moment when we compare it with the results of the James Webb Space Telescope. This is one of the iconic images taken by the Hubble Space Telescope, the pillars of creation, star formation within the Eagle Nebula. One thing to notice is not only is it very difficult to see inside these pillars, these are very gassy, very dusty environments, and dust tends to scatter visible light, which means although we can see the structure of these gas columns, we can't see what's going on inside. We can't see the stars that are presumably being born inside this rather dusty structure. If you notice over the entire image, we can see perhaps a few dozen stars. There are far more stars in this particular field of view, but we can't see them simply because of the amount of dust which is obscuring our view. And that's one of the reasons that when the Hubble produced lots of visible images, it was decided, wouldn't it be great if we could actually have a telescope that would work and actually see through these very dusty areas? Wouldn't it be great if we had a telescope that worked in the infrared part of the spectrum, which is less affected by dust? And that's why the James Webb Space Telescope was developed and ultimately launched in 2021. It has a much larger mirror. The hexagonal segment mirror in the center there, about 6.5 meters in diameter, is significantly larger than the Hubble Space Telescope mirror, which is of diameter only about 2.5 meters. So the James Webb Space Telescope with a much larger mirror is able to see fainter objects. But unfortunately, being large, it was a little bit difficult to get into space, so it had to be effectively designed, built, and then folded up, as indicated by the central panel here, before being put on top of a rocket and launched on Christmas Day 2021. Where was it sent? Well, it wasn't sent into Earth orbit, which is where the Hubble Space Telescope is currently sitting, orbiting the Earth once every hour and a half or so. The Hubble Space Telescope was sent to a parking spot. These red dots here are parking places in the solar system where you can place a spacecraft and it will essentially stay put. You might need a little bit of station keeping just to nudge it into the correct position now and again, but you don't need to continually burn fuel in order to keep them at those locations relative to Earth. So a number of different spacecraft have been sent to the locality of the so-called Lagrange point number 2, or L2 for short. That's where the James Webb Space Telescope is currently sitting and taking its data. The L2 point is approximately 1 million miles from Earth. The Hubble Space Telescope is only a few hundred miles above the Earth's surface, but the James Webb Space Telescope is 1 million miles away. Because it's working in the infrared, we don't want the heat to interfere with its instruments, and so we place it as far as possible from the Earth and the Moon with a sun shield that also blocks any light from the sun. So all heat from the sun or the Earth or the Moon is blocked by its heat shield. One of the reasons for building the James Webb Space Telescope, as well as being able to see the dusty environments of where stars and planets are being born, one of the reasons for switching to the infrared is to look back further in time. If we think of when the universe was created in the Big Bang, let's take that as 0 time. We are now sitting some 13.8 billion years later. That's roughly the age of the universe. But the universe is expanding, which means any light from distant objects is getting stretched as it travels from these distant objects to us. So the light might be a wavelength corresponding to visible light, but as it travels across the universe it gets stretched, and longer wavelengths correspond to infrared light. So it's thought that some of these very distant galaxies, because of the expansion of the universe, some of these very distant galaxies are going to be brighter in the infrared than they are in the visible, and hence the James Webb should be able to see even further back in time. Remember, the more distant objects, because of the finite speed of light, more distant objects, the light will take longer to reach us, so we're effectively looking further back in time. So by working in the infrared, we should be able to see objects further back in time, closer to the start of the universe. The numbers here in red, given by Z, are the redshift. By how much has the light been stretched? If the light is coming from our immediate neighbourhood, the light hasn't been stretched at all, a Z of 0. If the light has been stretched such that it ends up double its wavelength, in other words, it's stretched by the same amount as its original wavelength, we call that a redshift of 1, and so on. A redshift of 4 corresponds to even more distant objects. So how far back in time can we go? Well, what we would really like to do is to get back to this period indicating by these blue lines, these goalposts here, because we think that's when the very first stars and galaxies were born. Our Earth is about 4.5 billion years old. Our Milky Way is older than that, but we're not sure exactly how old. But we think the first stars and the first galaxies were probably born sometime in that blue period. Let's just blow that up so we can see it a little more clearly. Over a few 100 million years after the Big Bang, we think the first stars and the first galaxies were born. Now, in terms of how far back in time can we look, with a telescope like the Hubble Space Telescope, we can look back to approximately where the Hubble is indicated here. Maybe 500 million years, 500 million years after the Big Bang is about as far as the Hubble can go by looking in the visible part of the spectrum. But because by working in the infrared, we should be able to see galaxies which have had their light stretched from the visible to the infrared, then it's hoped that the James Webb Space Telescope will go back further in time and could perhaps push back that limit to the first 100 or 200 million years after the Big Bang. And what's interesting is to find out at what point are those stars born. We don't really know. We think all of the hydrogen will be present as soon as the Big Bang is over. In other words, 3 minutes after the Big Bang, we think all the hydrogen has been made, but it will take a while for that hydrogen to start to form stars. Will that take 100 million years? Will it take 300, 500 or more? We don't really know. That's one of the reasons for having these space telescopes, is to look back to this early period of the universe to help us understand how the universe came to be and how it evolved in these very early times. So the year after the James Webb Space Telescope was launched in mid-2022, it released a number of different images of local nebula as well as distant galaxies. One of its first images was revisiting the Pillars of Creation. The Pillars of Creation in the middle of the Eagle Nebula, as imaged by the Hubble Space Telescope many years earlier. And with a similar field of view, notice that now instead of seeing perhaps a few dozen stars, we are now seeing thousands, if not tens of thousands of stars. This is a reminder that by working in the infrared, we can see through a lot of the dust that was obscuring our view when we look in the visible part of the spectrum, and that allows us to get a better handle on the very dusty environments of how stars are born and indeed how early planetary formation occurs. When we look, for instance, at the dust around stars, this is a star in which the star itself is very bright and it's been blocked out by that central black disk in the middle there. By blocking out the very bright star, it's then possible to image these rather fainter, dusty rings around the star. And we think what we're looking at here is a planetary system in the process of formation. It looks like we've got a couple of rings. Perhaps this planetary formation is very similar to the way our solar system formed in its early stages. Maybe we're looking at something equivalent to an asteroid belt and perhaps the Kuiper belt of very icy objects in the outer part of our solar system. Perhaps this is an analogue of the same sort of thing. So we can get an idea of how our own solar system is formed by looking at images like this and looking at how other planetary systems form. By looking at distant galaxies, this is the so-called Pandora cluster of galaxies, not only can we see the galaxies themselves, these rather whitish objects looking rather fuzzy in the foreground, in the background there are these rather smaller red objects, some of which are looking a little bit distorted because the light from those very distant galaxies is being focused by the huge mass of this galaxy cluster. The light is being bent via a process called gravitational lensing, and that allows us to see even more distant galaxies. We're using nature's own lenses, if you like, to be able to see very remote galaxies rather more brightly than we would otherwise be able to view them. So both Hubble and James Webb are looking at galaxy clusters in the hope of seeing very remote galaxies and getting again an idea of when were these very early galaxies formed. James Webb has also revisited another nebulae that was originally imaged by the Hubble Space Telescope. This again is the Crab Nebula. This was imaged in the early 2020s, some 20 years after Hubble originally imaged the Crab Nebula. So if we compare the James Webb with the Crab, I'm going to flick between them. If you actually fixate on one particular structure, for instance that little structure there, these images taken by the James Webb and shortly taken by the Hubble Space Telescope have been very carefully aligned. So there's the Hubble, there's the James Webb. Hubble, James Webb. Perhaps you can see that everything seems to have moved slightly. So these images have been lined up essentially perfectly. So what we're looking at is the fact that this nebula is slightly larger as imaged by the James Webb than it is imaged by the Hubble Space Telescope. That's mainly because it was imaged 20 years later. This particular star went supernova, according to our calendars, about 1054. That's when it was recorded by people here on Earth. And so in 20 years, that's approximately 2% of its age, it should have grown something like 2% bigger. And that's what we're seeing when we compare the image from 20 years ago with the image of today. That difference in size is 20 years worth of explosion continuing to expand this nebula. The James Webb shows us something different than the Hubble. It's not just a question of size. The James Webb is able to identify not only what elements are in here, so that tells us something about the star that exploded. There's a lot of iron, there's a lot of nickel in there. It tells us about the elements that were inside the star just before it went supernova. And we can also get lots of interesting information. This wispy sort of structure here, perhaps you can see occasionally things that look like lines, a bit like cirrus clouds. We think those are electrons that are moving in the very intense magnetic field of the tiny neutron star that's been left behind after this star went supernova. So a lot of interesting science and a lot of interesting detective work on images like this to try and figure out what actually happened when this star exploded. Some, again, more recent data from the James Webb Space Telescope. This was released last year, or sorry, the year before last. It was able to image, again, by looking at a galaxy cluster, but in this particular case, looking at the very distant objects, as it were, behind the galaxy cluster. When we look in the James Webb Space Telescope, we see a very unremarkable galaxy inside that circle there in the inset. It's a very faint galaxy, but we think there's a black hole there because a different telescope, the Chandra telescope, which works in X-rays, is seeing a very bright object in that location. So if an object is very bright in the X-rays, but there doesn't appear to be an awful lot there, that's the signature that we're looking at a black hole, which is emitting very dramatically in the X-ray part of the spectrum, but we can hardly see it in the visible or infrared part of the spectrum. But we can see the galaxy, and we think that black hole is at the center of that galaxy. They seem to line up perfectly. And that's important because if we can see the galaxy, then we can measure its light and we can measure its spectrum, which tells us how far away it is. In other words, if we see how much the light has been stretched, its redshift, we can convert that from a shift in the light to how remote must it have been, or must it be now, in order to shift the light by that much. It's a redshift of 10. Its wavelength is now some 10 times larger than it was when the light left this object. So the James Webb gives us the distance, and Chandra tells us that this must be a black hole. So the combination of those two telescopes, when we take the measurements in combination, that tells us we're looking at a very, very early supermassive black hole, a very intense object, a very intensely emitting object at the center of this galaxy, but with a redshift of 10, this is very early in the universe. So black holes must have grown to be very large, even in the very early stages of the universe. And this has come as a little bit of surprise. A lot of astrophysicists have assumed that surely we will have to wait for billions of years before black holes form and then grow until they are millions or billions of solar masses in mass. And yet these observations from James Webb and Chandra would seem to indicate that black holes existed very early on in the universe, just in the first fraction of a billion years. How can that happen? We're not too sure. That's still a hot topic of research. Another thing that the James Webb is doing is looking for supernova in these very remote galaxies. And this is just to indicate that it can find an awful lot of them. They don't look very spectacular, even though they've been circled so you can see tiny dots in this image. The point is there are lots of them, and James Webb is able to see lots of supernova in lots of very distant galaxies. If it can measure lots of these objects and get an idea of how bright they are, it's going to test the idea that these supernova are standard candles. It is thought that when a supernova goes off, it goes off with a standard brightness such that if we look at how bright it appears, we can then figure out how far away it is. It's part of the way that we get the cosmic distance ladder sorted out to convert from redshift to distance. Now, if these are genuinely standard candles, then we can use them to calibrate and hence figure out what redshift corresponds to what distance. However, if we've got that wrong, if supernova are not standard candles, if every supernova doesn't explode with the same brightness, then our assumption about how we convert redshift to distance might be flawed. And hence the distances that we've been assuming up till now could be wrong. So it's quite important that James Webb does this survey and look at these various supernova to see whether or not they all seem to be the same brightness at the same redshift. There's still a little bit of work to be done, but if that proves not to be the case, that has serious implications for how large we think the universe is and how distant these very remote galaxies are. One of the observations made last year was this galaxy indicated by the arrow. There's actually two blobs in that inset, but it's the one indicated by the arrow that's the interesting one. This has got a huge redshift of 14, the most distant object yet observed. If we come back to our scale of what we were hoping for to be able to observe on that bottom scale there as far back in time as possible, the James Webb has now pushed us to the point we're now looking at Z equals 14. So we're looking at a galaxy that was about 300 million years old when it's observed. So we're not at zero, we can't ever get to zero, but we could in principle push that a little bit further. The fact that galaxies already exist so soon after the Big Bang, 300 million years, it already is telling us that we need to revise or at least refine some of our theories as to how stars and galaxies form. It might be that in a little while James Webb will see even more distant galaxies and will be able to push that even further towards zero. How far will we get? Only time will tell. There are other telescopes which are useful, not just space telescopes. The so-called Large Synoptic Survey Telescope, which is a bit of a mouthful, was renamed the Chamonix Survey Telescope. And the acronym LSST, which was originally used for the telescope, has now been repurposed to mean the Legacy Survey of Space and Time. This telescope, which is nearing completion and will be ready fairly soon, this is a telescope with an 8-meter diameter mirror, and it will be able to survey the sky such that it will be able to effectively image every object it can see every 3 nights, and it will keep scanning the sky night after night after night after night. So it will find out what's out there, and it will find out how things are changing. Remember, the Hubble Space Telescope has only got a tiny field of view, as indicated by the red rectangle there. If you want to survey the entire sky, well, using the Hubble, it would take you centuries to do that. If you want to survey the sky in days or weeks or months rather than in centuries, you need a much larger field of view. And the field of view of this LSST telescope is something indicated by that blue circle. It's actually too big to fit on this slide, but it gives you an idea of the size. It is many, many, many thousands of times larger field of view than the Hubble Space Telescope. How do you get that larger field of view? Well, you start with a large mirror, and you can see that this mirror is huge, 8 meters in diameter. And you also need a big camera. It's not sufficient to catch lots of light. You need a big camera. No, not that one. This is just a reminder that the sort of camera that you're used to using, the one in your mobile phone, is tiny, a few millimeters or so in size. On the same scale, the chip that's inside the Hubble Space Telescope in its camera is about it's about 4 centimeters. It's 40 millimeters on a side. It's a square chip containing 16 million pixels, and it's perhaps comparable to the sort of chip that you might have in your camera if you're a camera enthusiast and you've got a digital SLR camera or something like that. It's comparable in terms of the number of pixels, but the Hubble Space Telescope chip is a little bit larger. But the chip that's inside the camera of the LSST, by comparison, is absolutely huge. If we start with that indication of there's the 16 million pixels of the Hubble chip, the chip that's in the Hubble camera, let's imagine taking that chip and making it 9 times bigger by adding another 8 of the same. Then let's take that and add another 8 of those, and then another 12 of those, and then a little bit of extra silicon, which will be for focusing and for tracking. That is the size of the chip that's in the LSST camera. It is absolutely huge, 3 billion pixels. It's a 3 gigapixel camera, and it will be taking 15-second exposures and reading out in 2 seconds, which is a phenomenal speed when you think of how many pixels it's taking. The chip itself is so large I can't even show it to you directly. It's simply, there's only a tiny bit of the chip to scale. It is literally the size of a coffee table. I can't show you what that camera can do because it A, isn't operating yet, and B, I can't possibly show you an image with 3 billion pixels in it because my screen and your screen can't possibly show that many pixels. But just to give you a tiny idea of what it can do, let's just imagine what we could image in that tiny black square indicated there, a tiny fraction of the entire chip. If we imagine what we could possibly see, it might be something like that. That's a simulated image of what we could expect to get in a 15-second exposure. And we would be able to see, as you can see, many, many thousands, if not millions, of stars and galaxies. But this is only 0.03% of the entire chip. The entire chip would be able to look at many millions of galaxies and many millions of stars, and indeed would probably pick up thousands upon thousands of objects in the solar system in a single 15-second exposure. And this survey telescope will be taking pictures time after time after time after time for all night, every night, or at least every clear night. That will be most of the nights of the year for 10 years. This system is being built on the top of a mountain in Chile, which will have a lot of clear nights during a 365-day year. It might have 300 clear nights in which it will be imaging. And if that's what you can do in 15 seconds, just imagine what you can do when you integrate it all over 10 years. It will be looking at many, many stars, many millions, if not billions of stars within our galaxy, and it will be able to image many billions of galaxies. It will be generating catalogues of stars and galaxies, some of which we already know about, but many of which will be new to us. It'll be finding out what is out there. In a sense, we'll be taking an inventory of the solar system and an inventory of the galaxy and getting an idea of just how many galaxies are out there. One of the reasons, apart from generating catalogues of stars and galaxies, is to try and answer the big questions in science, such as this dark matter stuff. We think dark matter is out there because it's influencing the way objects are moving, such as stars in galaxies or galaxies in clusters. But we don't know what the dark matter is, and we don't really know where it is either. This is an artist's impression, indicating that if we look at a galaxy, do we know whether the dark matter is evenly spread throughout the galaxy? Is it clumped? Well, we don't really know. And one of the reasons that LSST is surveying the universe is to try and answer questions about the dark part of the universe for which we still don't understand what's going on. Back here on Earth, there will be even larger telescopes being built. The LSST is well on the way. We also have the European Extremely Large Telescope, which will be operational hopefully sometime around 2028 or thereabouts. You can perhaps get an idea of the scale by looking at the people out here at the front or the people standing on the gantry at the side here. This will be a true gargantuan telescope. A telescope with a mirror 40 meters in diameter. It'll be able to see objects that are much fainter with any of the telescopes we can currently use, simply because it can collect so much more light. If we go back to the original idea of the scale of these various telescopes, with Gran Telescopio at the top, the yellow indication of the currently largest telescope, and the space telescopes in the bottom left-hand corner, well, the extremely large telescope is shown here on the right-hand side. There are other telescopes of a similar size. A 30-meter telescope, for instance, is being planned on Hawaii. Is that the largest telescope we can ever conceive of? Well, not really, because people have said, well, why don't we just build one the size of that red circle? Well, the reason we don't build one the size of that red circle is not because technology doesn't allow us to do that. It's simply because it's rather expensive. And that's why they chose the extremely large telescope to be 40 meters, because it was simply within our price budget. But what would we call, if we did end up with a telescope that big, what would we call it? Because we've used names like the Very Large Telescope, and we've used names like the Extremely Large Telescope for the 40 meters. What would we call something which was 100 meters in diameter, which is indicated by the red circle there? Some people have suggested, well, we really ought to call it the Owl. Not because owls have large eyes, but because owl would stand for the overwhelmingly large telescope. A little bit tongue-in-cheek there. We can't possibly afford it. It's on the drawing board, but for the moment, even the extremely large telescope will be such a jump forward in terms of how much light it can collect. I'm sure we'll be seeing lots of interesting objects with telescopes of that size before we think about the next generation. So the bottom line is we need all of these telescopes. We need survey telescopes to look at the entire sky night after night after night and tell us what's up there and what is changing. And then when it finds interesting objects, it can tell space telescopes like the Hubble and the James Webb, go look at these objects in more detail. And it can tell telescopes like the Extremely Large Telescope, here's a really faint object. With your large mirror, you should be able to see more interesting detail because you'll be able to collect more light from these very faint and probably very distant objects. So with all telescopes like that, survey telescopes, space telescopes, large aperture telescopes, if they all work in concert, we'll be able to address some of the questions we have about the universe. And perhaps more importantly, it'll tell us which questions we haven't thought to ask yet. Thank you for listening.